Good afternoon, one and all. A warm welcome to everyone. Today, we have gathered for a webinar titled Energy Harvesting, which will be delivered by Dr. Pradeep Malaji, who is currently the Vice Principal R&D and Associate Professor at BLDEA's College of Engineering and Technology at Bijapur, Karnataka. So, in today's world, where we strive to derive clean and green energy harvesting is one area which aims to fulfill our increasing demands for the energy. And our today's speaker is a profound researcher who is working in this active area. So, here I welcome Dr. Pradeep to share his work and ideas in this field of energy harvesting. Yes, Dr. Pradeep, can you please
Okay,
can you start with the webinar?
sure. Thank you, Bhakti, for your introduction. So
Yes.
I'll be sharing my presentation now.
Okay.
Okay, can you see my presentation? My
Yes, Pradeep, we can see it.
okay. Okay. So let me start. Good afternoon, everyone. This is Pradeep Vimalji from BLD's Dr. PG Engineering and Technology, Vijaypur, Karnataka. Today, we discuss the concept of energy harvesting. In and energy harvesting that we see through this presentation, and what are the application areas, what exact mechanism that we are using for energy harvesting. So those things we'll be dealing with in today's presentation. So this might give you a flavor of what exactly the energy harvesting concept I am speaking about. Maybe you can take up this as your research if you're already working in this area. So we'll discuss about different challenges that are existing in particular, and what are the different application areas are open for this particular energy harvesting technology. I would like to thank Warhol University for inviting me to my presentation or talk on this energy harvesting area. Let me first of all wish all of you, and including me, the National Technology Day. I think way back in 1998, on this day, the nuclear missile has been tested by then Prime Minister Atal Bihari Vajpayee and our well-known APJ Abdul Kalam. So I wish all and everyone a happy National Technology Day, and let us contribute whatever we can do for national technology from our side. So coming about where I know and exactly where my college is located. So this is you can see. Let me change mine. Okay. So this is where I belong to. This is Vijaypur. Recently renamed as Vijaypur. Previously it was Bijapur. Now renamed as Vijaypur. This is north part of Karnataka. We BLD Association has several institutes, 75 institutions, and students, and which includes Indian College, University, and Army College. The institute is called in the main city of Jaipur and nearby. Studying tribology, nanoscience and material technology. Coming back to my inspiration, edge harvesting and IoT lab. Still, we are developing this lab, and we have got around $81,600 funds by BGST, which is for Canada. We have collaborating institutes, IIT Madras, IIT Kanpur, Shivnadar University, Lublin University of Technology Poland, Institute UK, University of College Dublin, and New Mexico State University, USA. Coming back to the main agenda of today's presentation or talk, the concept of energy harvesting. This will be the content of my talk today, which can give the gist or flavor of what exactly I'm talking energy harvesting in terms of. So we'll be starting with introduction. We'll go to the different mechanisms that convert into energy, and we'll discuss about what are the different challenges faced at present and how the researchers are trying to address those things, then their applications, and at the end we'll discuss about summary and future challenges and future directions. To start with introduction, we'll just start with the internet, then what is the current technological need, and what energy harvesting is. So we might ask a question of how this is related to internet. Why need to go through the internet? So let us start with internet, and we'll how it is related to internet. We'll implementation. So if you see the evolution of internet in pre-internet era, so only mobiles and telephones are at the most extent SMSs were the main communicating medias. Then once we started internet, we started using internet mainly at the basic email information or for entertainment, like YouTube, Gmail, Yahoo. These were the first stage of internet, which we started using for the content. Then started e-business or e-commerce, e-productivity. We started using internet for the services, so maybe Amazon, Flipkart, eBay, whatever. So these things started, like evolution started for service based now. We are using Facebook, WhatsApp, Twitter. So all these things is called as internet of people. So it's social media. We started connecting with people. So two persons can discuss, they can share online in the real time. The future are at the existing. We are talking in terms of internet of things. Why we need internet of things? Most of us know, and most of us we do talk regularly about internet of things. We need to identify, like in today's world, we want all the data on hand and in real time. For this, internet of things provides a solution where we identify, track, monitor, and share the data. What IoT is? IoT is all about of connecting all the things and have the real-time data in hand. The connecting things means what? We'll be using thousands and thousands of sensors. There are several problems which has been faced by IoT system. We'll discuss one of that problem and how to address that problem. Maybe there may be one of the options that we can discuss here for the IoT problem. What is current technological demand? What exactly we are like nowadays? We are mostly talking about smart cities. Even government of India and many European countries, they started implementing the smart cities. What exactly smart city means? We need everything to be connected and all the data has to be centrally processed and on-hand data has to be there. Like we want smart building, we want smart transportation, we want everything to be smart, smart healthcare, and these things to be interconnected and on-hand data should be available. So this all things require smart system. When does the thing become smart? When we connect all the things by the sensor. So we needing lot of sensors, wireless sensors. They are self-organizing, they are pervasive, they are small in size. You can see a lot of sensors which are small in size. The last question on wireless sensors is power. Whether the current is self-powered. So most of us say how they have been self-powered. Sensors, they have been powered by the battery, but they are not small. With a get the sensors of size, but the same development has been observed. Battery sizes and reduced the capacity. On the power the you the content that we are discussing today may be one of the solutions to make these sensors self-powered. We can relate that. We'll see how it is possible. We'll discuss what exactly energy harvesting is. We are ambient sources. It may be vibration, it may be solar, it may be radio frequency. we are surrounded by a lot of ambient sources of energy. So this energy can be transferred to generator as electrical energy, and it can be either stored or directly utilized, or stored and utilized whenever it is required. Mainly you are targeting for the electronic devices. If I say electronic devices, a lot of electronic devices. So where exactly the application here comes into existence. The output that we are getting with that, we're able to at present we can power up these electronic devices which requires power input up to 1 milliwatt. I repeat, 1 milliwatt. So why this is required? So first reason is health concern. If you're using batteries, so batteries are made up of lithium, which are hazardous to the nature or environment. And so these batteries needs to be frequently replaced. Facilities, we have some unaccessible areas where it is difficult to frequently visit and change the batteries. So applications of these biomedical wireless sensing, we will discuss this at the end of this presentation. What exactly application areas are there? To compare this battery technology and energy harvesting technology, so with respect to time, you can see at the initial point we have high power input in the battery. As the days goes on, we can see a reduction in the power availability. Mostly, many of the batteries they last long for around 1 year. After 1 year, we replace. But if we take energy harvesting technology from the rest of energy harvesting technology, so we can use the ambient source and we can convert it into the electricity and we can use it again. Can use it. We can have energy and use it, store or whatever. So this cycle keeps on repeating. We can say theoretically infinite, but it has also has some limitations based on the type of material that we are using. So we'll be discussing what are different mechanisms and how exactly this is done. Next slide. So context of energy economy. So they are actually dealing with. We know when I say energy harvesting, most of you might have thought, okay, maybe hydroelectric or mechanical or thermal those things. This harvesting is not a new phenomenon, has been there since the evolution of this industry. Usually, what mechanical energy harvesting, maybe wind, thermal, whatever. So they're in terms of large scale. So in terms of megawatts. Then come if you take this gensets, so they're in terms of watts. So what we'll be talking today will be in terms of micro scale. I think in the previous slide I showed that I repeatedly told it is milli to microwatt. Maximum is 1 milliwatt that we can harvest the energy from this technology. So this is micro scale, and also we have the device in terms of millimeter size. Also output what we are getting in terms of micro to milli or sometimes even up to ultra watt per centimeter cube. So this is miniaturization, and this miniaturization is required for the IoT application. What are the different energy levels or like different ambient sources we have discussed in the earlier slide? From which source we can get how much of the energy? If it is photovoltaic, we can expect an output of 10 milli up to 10 milliwatts per centimeter square. If it go for vibration, it is in ultrawatt or some milliwatts, 1.4 ultrawatts to 1 milliwatt, we can harvest energy from vibration. We can consider thermal, where we can get the highest output up to 20 microwatt. Also, we can harvest energy from radio frequency, where we can get output of up to 0.1 microwatt per centimeter square. These are different scales we can harvest energy from the ambient sources that we discussed. Next, going to mechanism, we discussed what exact energy harvesting and what are the types. We'll discuss this mechanism one by one, and there are many mechanisms we'll be discussing which communities. Mainly, I work on device energy harvesting, and recently we started working on thermoelectric generator university. We'll be focusing mostly on vibration energy harvesting, and we will discuss different technologies available and different challenges with vibration energy harvesting. Just have a look through what exactly is thermal energy harvesting. Most of us we already studied this feedback effect, and when we have one source as a heat source, there is a potential difference. Due to this potential difference, there is a voltage difference. Same thing we can use, and we can generate voltage, and can be used for the sensors. Higher the temperature difference, higher will be the output. That's what we can see in this graph. As the temperature difference increases, we can see there is an increase in the power output. Similarly, there is an increase in voltage as well as efficiency of the device. This is how thermoelectric energy harvester works. Then coming on to vibration energy harvester, we have vibration source. So with that, we will have the vibration energy harvester or energy harvesting. We have mainly 3 or 4 different methods by which we can convert vibration into electrical energy. We know almost all of these things: electromagnetic, piezoelectric, and electrostatic. How these things work, we will see in the next stage. Once we convert these into electrical energy, either we will store it for the future use. Sometimes it will be directly utilized for the devices. Okay, so we'll discuss one by one here. So what exactly those terms means. The first one is electromagnetic energy harvesting. We know that it works mainly on the Faraday's law. We have mechanical part and electrical part here. We'll have the coupled equation, electromechanical equations. We know that whenever a magnet moves in the coil, the different potential difference is formed, and we can generate the voltage out of that. So this is how we harvest energy from the electromagnetic mechanism. Similarly, we take piezoelectric here. Piezoelectric is one of the circuit here, where both the ways are possible, either mechanical to electrical and electrical to mechanical. So we apply mechanical input to the piezoelectric field, that will be converted into electrical output. If you apply the electric input, it can be converted into mechanical strain. We are using the reverse effect, that is mechanical to electrical. This is how piezoelectric energy works, and we know what electrostatic is. Capacity, which causes the voltage or to increase. These are the 3 various ways where we can convert vibration into electrical energy. All these technologies have their own advantages and disadvantages based on requirement, space, or we can decide which generation method has to be utilized. If you take electromagnetic, it is not a small material and it doesn't require to operate. The problem is that it requires a lot of space. We need to test. Usually, electronic device requires big size. It's a budget size. There is some difficulty in this with men. If you go to it, it is also not a small material, but it is small with men. These are each not if you these different data, it has advantage of comparative men. The problem is after use they get depolarized and used, and this material is very little in high vibration. Similarly, material is has high coupling or high coupling coefficient, which means that the condition of electric, there is no question of people in case of electric, but we have Okay, sorry for interruption. I think there was an internet problem. We'll be just briefing about all these things, and I'm not sure where I left actually. We'll just quickly go through these things. What exactly, like we are discussing about energy harvesting concept, what exactly energy harvesting and where it is required. So we have seen this. Why? What exactly is Internet of Things? That is the evolution of Internet. Presently, we are at this Internet of Things era where we need a lot of sensors, which needs to be powered up, and that powering up solution can be through this energy harvesting, which can replace the batteries. We have seen why we need this exactly IoT. This is for the smart cities. What exactly is energy harvesting? We are surrounded with a lot of ambient sources of energy. It can be converted into useful electrical energy by using generator, which can be used for later, or which can be stored or directly used for the electronic devices later. The range that we are discussing will be in terms of up to 1 milliwatt. So this can reduce, it can give solutions to many of the problems. One is health concern. You can reduce the use of lithium batteries. You can reduce the frequent changes of batteries. So in some places where we have accessibility problem, there also it is one of the good solution to use the energy harvesting. Also, application wise, we have a lot of areas where this technology can be used. If you compare the performance of battery with harvester, initially we have high power input in the battery, but as the time passes, maybe at the end of first year or 1 year, so the amount of power left in the battery is almost zero. Comparatively, when you go for the energy harvesting devices, so it has low power, charging up and charging down. It keeps on repeating cycles. So we can use it for, theoretically we can say, infinite. But again, that depends upon the materials that we are using. If you talk in terms of energy harvesting taxonomy, what we are discussing today, so there are three types. One is mega scale, meso scale, and micro scale. So large scale energy like wind power, which is in terms of megawatts, thermal, wind stations, all these things are in the category of mega scale. We have meso scale like our gensets, which are in terms of watt per centimeter square. We are discussing about micro scale today. Our application is related to this micro scale because we are mainly focusing on IoT, which needs a lot of small sensors and miniaturization. There are different energy harvesting technologies. One is photovoltaic, vibration, thermal, radio frequency. They have different range of power output. Photovoltaic has power output in the range of 10 micro milliwatt, and vibration is up to 1 milliwatt. Thermal, it has up to 20 microwatt, and also radio frequency, which has in terms of 0.1 microwatt per centimeter square. Different mechanisms available. We'll be discussing. We're limiting our discussion to mainly to the vibration energy harvesting, and we also just go to one slide about what thermal energy harvesting is there. We recently started working on it. Thermal energy harvesting. So we know this Seebeck effect. We have two junctions, one hot junction and cold junction. There is a potential difference. So using this potential difference, voltage can be generated. We know that here, as the temperature difference increases, there will be an increase in power output. Coming to the vibration energy harvesting, what exactly and how exactly it works? We have the vibration source here. We have different vibration energy converters. So mainly we have electromagnetic, piezoelectric, and electrostatic. Using these three technologies, we can convert mechanical vibration into electrical energy. Then this can be stored and can be used for the devices. How these devices work? We know most of these electromagnetic. It works based on the Faraday's law. We have a magnet here. We have the coil here. This magnet moves in the coil we have the EMF induced by which we can generate the voltage. If you see the mathematical point of view, we have the two equations here. One is mechanical part, second is electrical part. Similarly, we can replace this electromagnetic with piezoelectric. This is one of the smart material. We know what exactly is piezoelectric material. It can convert mechanical input into electrical output, and reverse also is possible. Electrical output to the mechanical output. We'll be utilizing one of them. Here, what our agenda here is convert the mechanical input into the electrical output. And how this electrostatic works? It works based on the change in the or variation in the capacitance. So all these technology has their own advantages and disadvantages. So based on our requirement, we can use one of these things to convert the mechanical energy to the electrical energy. If you consider electromagnetic, it's not a smart material, but it requires heavy space, bulky space. Electrostatic, it also is not a smart material, but it requires external voltage to start with. Piezoelectric is one of the smart material, but it has problem of depolarization and is very brittle. There is chances of failure of this piezoelectric material. Similarly, magneto-restrictive, it has high coupling coefficient, but it has non-linear effect into it. So we can select our own transformation method. So based on requirement. Coming on to this linear energy harvesting, like this is a conventional energy harvester which this research started. We already studied this particular system, spring mass system, subjected to external force. So this frame is oscillating at certain frequency, okay? And we have the spring mass system, and this spring mass system has its own natural frequency. Whenever this frame oscillates at the frequency of the spring mass system, that means whenever spring mass system frequency matches with the frame oscillation or frame frequency, we say that as the resonance. At that point, we can see there is a high displacement of the spring mass system, and we can clearly observe here at the resonance where both the frequency matches, we have the high amplitude. Similarly, we can plot the power output curve. This is power output. At the resonance, we can get the high power, but away from this resonance, the power output is very less. There is a reduction in the power output. So this phenomena we can say either whether it is electromagnetic or piezoelectric, only magnitude will change, but the nature remains same. At the resonance, we will get the more power output. There are challenges here. Let us discuss those challenges. What are the challenges? First thing what we have seen is only one peak we are getting, that is single frequency power generation. We are able to generate power only at the single frequency, and that maximum power is only at the resonance. Away from resonance, it's very low. And also, some present conventional harvesters, they cannot operate at the low frequency. So these are the challenges needs to be addressed so that we can have a good performing harvester. So this is the challenges posed by the existing conventional harvesters. Many researchers are working to address these challenges. We'll see some of these methods by which they started, or they are able to come out with the new solutions to meet these challenges. So what we want is, we don't want energy to be harvested only at particular point. We want at multiple frequencies energy is to be harvested. So by and large, we can say we want to increase the frequency band of our energy harvester. So that is, we can say, band enhancement. What are the different methods available right now? We have various methods. One is multi-mode harvester or array of linear harvester. We have non-linear harvester. Also, we can go to the electrical solution. We will not be discussing on this part. This relates to electrical, as this energy harvesting is an interdisciplinary work. It requires both mechanical part as well as electrical part. So we'll be discussing these two methods here. Electrical part, I'm not an expert in this particular field, and we are looking for some collaborators on this area. We'll be just limiting our discussion to these two methods. If you take multiple or multimode harvester, okay, what we can see here is we can see multiple cantilever type of beams here, beam 1, beam 2, like there are n beams here. We can see a difference in these beams. So first beam is having more length compared to the last beam. There is a change in length of beam. What happens if we change the length of beam? So these different beams will have different natural frequencies. So that means first beam will produce maximum power at this particular frequency. Second beam produce maximum power at this second frequency. So at different frequencies, each beam will contribute and they will have the maximum power. By this, what we can do is we can harvest power at higher frequency band. For example, if our host structure, we consider a bridge as a host structure, it has its own frequency, like whatever frequency is that. But for that, if you want to harvest the energy from that bridge, we need to design our harvester which should match the frequency of bridge. A certain slight deviation will reduce the power output. So there is always uncertainty. We are not sure whether bridge will be always be exciting at a particular frequency only. There may be error in the measuring device also. In order not to take the chance, what we can do is we can go for the broadband energy harvesting. We'll have, instead of only one harvester, we'll have multiple harvesters which are operating at the different frequencies. Even bridge is not vibrating at first frequency, it is at second, then our second beam will harvest the power here. But there is one more option. Instead of going for multiple harvesters, we can go for the multi-mode harvester. We know that a continuous system will have the multiple modes. If you take this as simply supported beam, first mode will be at the center we have the maximum bending or maximum displacement here. So this can produce maximum output, power output. Similarly, if you go to the second mode, first and last will have the maximum amplitude. In the sense, they will produce maximum voltage output. At different modes, different harvester will produce power output which is maximum. Here also we are carrying range of frequency. There is one more option. We can go for the hybrid harvesters. Instead of going only for the piezoelectric or electromagnetic, we can combine both of them and harvest the energy. Another option that we have is the non-linear harvester. If you see this, it is something similar to levitating ring or levitating magnet. You see here, like at the bottom I have a magnet with north and south pole. At the top I have a magnet north and south. The middle magnet has repulsive interaction with both of these two magnets. That means this middle one is always be levitating. So due to this magnetic interaction, there will be a non-linear effect coming into picture. What can along with that we have the magnets here. This also has repulsive. So between these two magnets, this middle magnet can oscillate here or it can oscillate here. It has two stable points. Thus, we'll have the maximum power output when it can travel from this point to this point. It covers the entire coil and it can harvest the maximum power. This is the non-linear effect that you're getting into. Or we have another option. We generally know it as duffing oscillator. We have a beam and magnets here. This is a metal beam, a magnetic metal beam. Or we can have a magnet attached here, due to which there will be a non-linearity induced. Or there is one more option. We can go for the buckled mode energy harvesting, which will be bistable. Whenever if we go beyond the critical mass of this particular buckling beam, we can see there will be a bistability coming into picture. What it does, usually all these things, what they represent, like if you draw the potential well here, you can see two potential wells here. First potential well and second potential well. So either beam can oscillate in this range and first potential or second potential. So voltage output will be very low. Whenever beam is able to oscillate or there is an interval oscillation between these two wells, we can see a large amplitude here and therefore there will be a maximum power output. If we draw this, we compare this with the resonance curve or if we say a frequency response curve, we already know how the response curve looks for the linear. Only at the resonance we get the highest power. With introduction of non-linearity, either we have the softening effect or hardening effect. It's a bending towards low frequency or high frequency. So in both the cases, what we can say is we can cover a large range of frequencies where we can harvest the maximum power. So by this, we are able to harvest the power at the higher bandwidth. Even with this magnetic dumping oscillator, we have different magnetic combinations can be taken into consideration. With that, either we can get monostable, bistable, and tri-stable harvester. Like if I have a magnet here, and these two magnets, if these two magnets are attracting, we can see oscillation here. There will be oscillation, and also oscillation between this magnet and this magnet. That means there are two stable, and at the center it will be unstable. It will be bistable system. Similarly, I can attain tri-stable based on the different combination. So these combinations will lead to the higher output. Okay, if we consider example, piezoelastic here represent just a linear system. Piezomagnetoelastic represent a non-linear system. If you consider in terms of voltage, it's the input, it's the acceleration. We are mostly worried about the voltage output. This one, which is piezoelastic, which represents linear system, we can see that at the lower frequency, so it is giving minimum voltage output. Only at the resonance, it is giving the highest power output. Again, it comes down. But whereas this piezomagnetoelastic, which is non-linear harvester, at beginning only, it has high voltage output. Only it lags behind the linear harvester only at the resonance. At resonance, only this linear harvester is outplaying the non-linear harvester. Otherwise, non-linear harvester performance is better than the linear. So this has led researchers to look more into this non-linear harvesters, which can give the maximum bandwidth. There are also possibilities that we can, okay, why only one non-linear harvester? If you use two, what will happen? So we have seen a little bit enhancement, and there are various possibilities of this one, and also there is an increment in the power output too. Like this is the area where I actually worked on. Instead of single harvester, I used pendulums, two pendulums naturally which are non-linear based on the amplitude. Along with that, what we did is we used a mechanical coupling, also introduced an magnetic coupling. These two end masses are magnets. There is a magnetic interaction between these two pendulums, which induces the non-linearity. What we are considering here, we are considering two coupling here. One is mechanical using spring, and second is coupling due to the magnetic interaction. What we observed that if both couplings are present, the power output is more compared to just having magnetic coupling or just having spring or mechanical coupling. If both are present, performance is better. Similarly, people have worked with piezoelectric harvesters also, where they have used multiple nonlinear harvesters. You can see a magnetic interaction between these two beams, okay, and these are the PZT patches. Similarly, they used beams in opposite direction, and they use the magnetic interaction here. These two are the magnets. So multiple harvesters have also shown improvement in the bandwidth as well as power output. But there are also some limitations. Only one of these harvesters can harvest the maximum power. If somebody is interested, we can discuss this in later stage. So coming on to the actual application, if you can see this, I have two videos here. The first one, okay, this represents a model of the building. At first video, what we can see is this is a building, and this is actually a pendulum, but it is constrained not to have any motion. Now it is just acting as mass to this particular building. So this is oscillating. Now we made it the pendulum to oscillate, and also the frequency of this pendulum is equal to the frequency of the building. What is happening here? You can see that this first one without pendulum effect, it is oscillating for higher time compared to with the pendulum effect. This is known as tuned mass damper. So what actually we want here is we want to reduce the vibration of the primary system. We want to reduce the vibration of the building structure. So this is controlling the primary system. This is secondary system. There is also, we know that dynamic vibration observer, it works on the same concept. So is it possible to harvest energy along with controlling this primary system? Answer is yes. We know that in this case, secondary system is oscillating. We can have an electromagnetic system here and harvest the energy from this. Why this energy is required? So most of the structures, the risk is when they are subjected to earthquake. When it is subjected to earthquake, most probably there will be a power failure. We will not be able to have the power, and we will not be able to supply this power to the sensors to record the data or to get some data. We can harvest this energy whenever there is a earthquake. That harvested energy can be supplied to the sensor to get the data. So these can be useful for in the case of disaster condition. We'll just quickly go to this mathematical model. This is similar to the previous one, but only thing this is a dynamic vibration observer. This is the primary system. This is a secondary system. If you take any vibration book or basic vibration, if you go to the 2 degree of freedom system, you'll be reading one thing as dynamic vibration observer. Primary system, secondary system. Only additional thing here is this piezoelectric element part. To the secondary system, we are attaching the piezoelectric part. Now, first and second, this represents mechanical equation. Primary system, secondary system. This is the electrical equation. This effect of this electrical factor on this control of the primary system. What we want is the vibration of the primary system has to be reduced at the resonance. With increase in that coupling factor or factor of electrical coupling, we can see there is a reduction in the primary system vibration at the resonance. At the same time, we are able to harvest the power out of it from the secondary system. But there needs to be an optimization because both are not like, it is not a win-win situation here. If you are reducing the vibration of primary system, there will be reduction of the voltage output also. If you want to increase voltage output, you have to compromise with the vibration of the primary structure. But our main agenda, primary motto is to reduce the vibration of the main structure. But we need to find out an optimal way out of this. So we need to find out the optimal parameters where we are able to reduce the or control the vibration of primary system, also to get the feasible amount of voltage output from the secondary system. So this is what we worked on. It is similar to the previous one. This represents our building system, primary system, spring and damper, and this mass, and this is the pendulum. Here also we have seen that there is the effect of coupling, electrical coupling on the control of primary system. Also along with that, we are able to harvest the power from secondary system. One step ahead, nowadays you might be hearing a lot about of metastructures. We can use multiple repeated structures of secondary system to reduce or to control the main structure, and also along with that we can harvest the energy. Okay, coming on to the application. Okay, real-time application. There are already particular products into the market which have some application. If you can see the first picture here. Let me change. Okay, you can see this. So this is some wristband is there, but this wristband has some sensor into it, and it has also a harvester. It may be TEG or it has TEG into it. Or sometimes you can use also piezo patch here, flexible piezo patch. Either TEG or flexible piezo patch, TEG generates energy because of the temperature between difference between the human body and outside. Or if you have the PJT, whenever your wrist motion is there, so PJT converts that motion, kinetic motion, into the electrical energy. So that will be supplied to the sensor, which can measure pulse of the patient, and data will be sent to the concerned doctor. So doctor will be having on hand real-time data of the pulse rate of the patient, and based on that pulse data, doctor can take a call or decision. Whenever there is an emergency, he can directly call the patient and contact the patient to take some medicine. If you see here, this is a shoe. This shoe is attached with these harvesting devices. Whenever you keep walking, so we can produce the voltage output. This can be used for some, maybe mostly in case of military applications. They keep walking and they need some electronic devices to be charged continuously. So this harvested power can be used to charge up the electronic devices, or they can charge the battery also. So you might have seen in some videos where the people are working on tiles and they're able to power up some lights. So those ceramics are embedded with piezo. They are known as piezo ceramic tiles, piezo ceramic tiles, where there will be a piezo inside the ceramic. Whenever you put your step onto it, it will harvest the energy. So this we can see, this is a pacemaker. This is the heart. It's not a human heart. It's not actually uh, in application right now. This is the animal heart. They tested this particular animal heart, and this is the pacemaker. We know that usually this pacemaker to be in operation, it needs a power supply. At present, what we are doing is we are putting a battery along with this pacemaker. Usually, life of this battery is 4 years to 5 years. That means after every 5 years, patient has to undergo a surgery, and that battery has to be replaced. So, which is not suggestible in some conditions if patient is critical or he has some side effects of some side diseases, or if he is very aged, it's difficult to undergo surgery. What researchers have done, like instead of battery, what they did is they have harvested energy from the heartbeat itself, and that has been supplied back to the pacemaker. But still, it is in research phase. It is not yet has been tested for the human body. This is the some animal heart. Similarly, we have the battery remote control. So this Philips remote control completely works on energy harvesting devices. There is no battery at all. Usually, our remote control have two batteries. That space has been used to install harvesters. So this can consist of multiple harvesters. One can be from solar, one from vibration. So they have been integrated and it keeps on working without replacement of battery. If you see the market capacity, what is actually application? If you see from in 2017, there has been a market of 1.5 billion dollars. So it is expected to increase by fourfold by 2022. What are the sectors this energy harvesting is covering at present? So it is consumer electronics most probably. It also covers military application, aerospace application, wireless sensor network, industry. We are talking about IIoT, Industrial Internet of Things. It plays an important role in IIoT. Also, some portion of mobile phone charging, laptops. So work is going on. Also, healthcare. So different areas where this energy harvesting is finding its application. Coming on to the summary. So what we have seen is there is something like energy harvesting, which can be stored, which needs some power management, cycle management, and there are different techniques by which we can convert the energy harvesting. There are various techniques. We just discussed one or two here. With this, we have a lot of challenges. We need to go for low cost harvesters. We need an optimization when we want to go for control as well as energy harvesting. We need harvester management. Electrical part is yet to be like what happening presently is that mechanical people they are working separately and electrical people are working separately. There needs to be a collaboration between mechanical and electrical so that we can come out with a complete product. What I work, I do a mechanical part. I'm saying that open circuit voltage is this much. But once in actual application, there will be losses, all those things, and we need power conditioning. So this I can do only if I can collaborate with the electrical. If anybody from electrical background and they're working in this area, so I'm open for collaboration. You can just send me a mail. At the end, I'll be sharing my mail ID. What is there in research? What are the challenges? Where we can start working on? So we need to work. If you want to work, we need to work on how high power output, how to increase the power amplitude, and also reliability and robustness. As I discussed, PCT is mostly brittle. If it undergoes large amplitudes, it will break. And not only that, we need to install these harvesters on the host. We need to make sure that it is robust, it can withstand the vibrations of the host, impact, sometimes impact load will be coming. We need to work on these things. There are future challenges nowadays. Many of the people they are talking about metastructures, which I shown one of the figure. Also, IoT application, how to bring actually this technology into the IoT. So then we need to connect the sensors, data collection, all these things need to be addressed. There are a lot of vast areas there where we can choose to work in this particular energy harvesting. If you see the market, most of the harvesters, and if you compare density wise, vibration harvesters has high density compared to thermal. Thermal has a high output, but in the market, this T is available, thermoelectric generator. You can order it, maybe costing around 200 rupees. It will be of size 2 centimeter by 2 centimeter. Usually, density wise, vibration harvesters are better compared to thermal. But again, as I said, it depends on the application. We can decide which one we should take, and most of the times it will be hybrid. So these are the references like from where I've taken most of the materials. So I should be thanking all my collaborators, like maybe Dr. Ali from IIT Madras, who happens to be my research advisor. Also, Dr. Professor Fritzell from Science University UK, Professor Prakashi, Vikram Prakashi from Ireland, UCD, Abdul Kasey from New Mexico State University, USA, Professor Sandipur Adhikari from Science University UK, Professor Litai from Poland, Tanmoy from IIT, and Venkat from Shivanagar University. Also, I should thank my students working under me, Ravindra and Najim Makandar, and some BTech students from Shivanagar University. I should thank all these sponsoring funding authorities. One of the funding is for few of my research. I got some funding from EST Develop of Poland government. Then I should thank for your patience hearing. Also like to thank Bhakti for inviting me and delivering this particular lecture. If any questions, as I heard, there will be no question answer session here, but you can always reach me at this particular mail ID and you can send your queries. And if somebody is interested in collaborating and open to collaboration, we can work together on this particular area. Thank you.
Thank you so much, Pradeep. It was really a very informative session from your side. And yes, there was some problems related to internet, but then still we managed to come back and deliver the webinar nicely. So a very big thank you for you and for your valuable time and efforts towards delivering such a nice and wonderful session. And once again, I would like to thank you on behalf of the Dean, Dr. Unnati, Principal Sir, Dr. Vipul, our Mechanical Department HOD, Mr. Imran Maulvi, for this wonderful session that we just had. Thank you so much.
Thank you. Thank you very much.